Okay. I updated the lecture notes significantly, but still in the process of editing in chapter chapter 10, section 10, which I'm going to talk about today. So we are talking about the type 1 string theory, type 1 theory. That is the Oriental projection. Unfortunately, it's a bit it's better for at least better for yeah for recording. So as I mentioned, there's a so type 2A, type 2B. So we introduce and the related TDRT. And then today we'll introduce type 1, which is the Oriental projection, or maybe schematically omega I'm going to use. And then I will use next lecture I'm going to introduce heterotic SO13, heterotic E8, and then last I'm going to introduce 11D theta. So we are going to how to say, is it clockwise? Yeah, clockwise way to introduce 5 type of string theory. And this, so we are going to introduce third type of string theory for now. Okay. So far we have considered. So type 2A is the type 2 theory is the oriented string theory. Oriented means the worksheet is oriented, and then worksheet is oriented, and then what? So the without D brand, we only have closed string. On the other hand, so with D-brain, one can introduce with D-brain, one can introduce the open string. From now, so we are going to introduce type 1 theory. Is the unoriented. Worksheet. Including unoriented worksheet, and moreover, it's open string. Open string theory. And then, as I mentioned, so that it has 32 supercharges, but this one's 16 supercharges. 16 supercharges. And then the reason why we have 16 supercharges, we introduce so-called Oriental flip operation. So Oriental orientation flip operation. And then often this one is called all plane, Oriental. Oriental or all plane. So, moreover, so here what we have seen is with D brain will give rise to UN gauge group, and D brain will give rise to UN gauge group. On the other hand, once you introduce the all plane, one can just from all plane one can have SON or SPN gauge group. And in particular, so type 1 only has the type 1 theory is only the gauge. So it's only consistent only with so we will see SO32 gauge group. That's what we are going to see. Okay. So that's what we're going to see. And mainly, even though we're talking about superstring, the full element, how to say, for the sake of simplicity, I'm going to talk about first a bosonic string, how on bosonic string, oriented omega on bosonic string. That's we are going to see. So omega is indeed for cross string. So omega is something like is mapped to just spatial direction orientation flip. B and C is also same. So that's how they change the another orientation flip operation. And the model expansion is much more clear. You just holomorphic or left moving, holomorphic alpha n to another holomorphic one, or right moving to left moving. Okay, that's how the orientation flip operation. So what we are going to introduce is essentially we just introduce the this operation, keep state states invariant under 1 plus omega over 2. That's orientation. Let's say orientable projection. So that's called orientable projection. Then, so as you can see, bosonic string. So the tachyon is intact. Tachyon is intact under this operation, but for cross string we have the symmetric guy. action. So this is graviton, and the B field antisymmetric by and then you have dilaton. So for massless, these are massless, as we already seen many times. Yeah, trace of so that's the, so as you can see, so if you swap alpha and alpha bar, the graviton stays the same, is okay, but here it's antisymmetric, so you get the minus sign, and they cancel. So 1 plus 1 minus 1 is equal to 0. So therefore, this one is projected out. So this one is projected out, and then so B field is in B field is absent on the this Oriental projection. So tachyon, graviton, and dilaton are okay, but B field is projected out because of the you just swap. You need to exchange the right moving and left moving, or holomorphic and anti-holomorphic. So as I mentioned, so F1 fundamental strength is and its fibrine electrically coupled to so this is electrically and this is magnetically coupled to B field, B mu nu. So since B mu nu is absent, so therefore this means that the cross strength is unstable. Unstable in the with Oriental projection O plane. So let's look at the. So then, what about the open string? So open string is also very similar to what we have seen over there. The so open string as a cross string, the sigma is inside of 0 and 2 pi. But here, open string sigma is 0 to pi. Okay, 0 to pi, and then the for worksheet. So the orientation flip is indeed, you just have t pi minus sigma and so on, and what's left is the same. Instead of, I mean, it's almost same as cross string, but you have to just be careful about the range of sigma. So this will, if you do the model expansion, this will change a little bit about, oh yeah, I have to explain. So open string, you have to specify boundary condition. Yeah. So you have to specify boundary condition, and then in the presence, so here we assume the open strings with Neumann boundary condition. Neumann boundary condition. So in other words, so we assume there is a so-called imposonic string D25 branes is present is a bosonic string, or a superstring D9 brane string is present. They are not dynamical object. So it's a space filling. So this is space filling plane. Space filling plane, so that the open string can move around with Neumann boundary condition. So that's what we are going to assume. In that case, the mode is this is a good exercise. I mean, as you have done in homework 1. So it's if you impose this boundary condition. So this is what you end up with. B and mu is and C and mu. I mean, it's quite amazing. I mean, it's quite amazing how the string theory works. It's amazingly working. And then, as you can easily see, if you try to do the same operation as before, 1 plus omega over 2, of course, I mean, minus 1 over mu acts on the K will give you gauge boson in the bosonic string. But of course, minus 1 is minus, I mean, you get a minus sign. It seems like naively thinking you just project it out. But somehow, as I mentioned, quite amazing that the pioneering people who construct the string theory is miraculously somehow string theory working. And so we can just recall that for open string we can introduce the Trumpet degrees of freedom. So as I mentioned, so you have a bunch of state acting on open string vacuum, so the level is n, k, and furthermore we can introduce I and j, right? I and j are the Trumpet degrees of freedom. Trumpet degrees of freedom. So, and the orientation flip is the so orientation flip essentially you have the open string, and this is t direction, and this is sigma direction, and the sigma goes to pi minus sigma is essentially you just flip the orientation to the, I mean, of course, in the reverse direction, and that's why. So therefore, the n is reversed. Okay. So therefore, omega is swap I and j. So Trumpet degrees of freedom is coming from one end and the other one, I and j. Okay, recall that. So therefore, I and j is swapped. Okay, so therefore, you can incorporate. You want to incorporate. So now, of course, n is just given by alpha minus whatever 1. And 1, alpha minus 2, and 2, acts on 0k, right? 0k, and the level is n. Okay. Level is n. So therefore, the act. So let's call, and you can include the gauge indices Tij, which we call n, k, t. Okay, so this is the Yang-Mills, Lie algebra generator, Tij. So then omega acts on n, k, and t is indeed, you just swap I and j, so therefore this is, you get the minus 1 to the n is really coming from here. On the other hand, the gauge index is taking the transpose. Okay, so you just have a transpose. So therefore, to have the Oriental under the Oriental projection, T has to be symmetric for n is even, and T has to be anti-symmetric, n is odd. N is odd. Okay. And in particular, the gauge field, as I mentioned, is coming from this one, this guy, gauge field. Coming from this guy is level 1. Therefore, for gauge field, it has to be, so level n is 1 for gauge field, so therefore Trumpet factor has to be antisymmetric. So this will give rise to SOMB algebra. SOMB algebra. So this is what you get from the how you obtain it. So this, as I mentioned, so with our Oriental, you get the SOM. So what about the SPM? Of course, that's a natural question one can consider. So to introduce SPN, so we again introduce something more non-trivial things on the Trumpet factor. When Nk acts on Trumpet degree of freedom, what you get is the -1 to the n, so that comes from just over there. But so we just transform under non-trivial metrics involved also. So of course the open end is swapped, so J and I are swapped, but with some metrics. Oh, sorry, this is inverse. With some P is the some matrix which is in here. And once imposed, Oriental projection has to be, if you apply twice, it has to be equal to 1. Okay. So if you apply twice, what you would get is n k I j is equal to p pt p inverse. So pt p inverse n k I j. So I prime and j prime, and then pt p inverse inverse. So that's what we get, and then here we have something like a I and I prime, and j prime. That's what we. So once you apply twice, what you would get is this guy. How did it work? I think I hope I'm correct. I did computation. Let me check my computation. This is correct or not. Let's see. Let me check my computation. So in lecture note was simplified. I think I just keep my computation in the lecture note. Otherwise, I will make a mistake in later. Yeah, I think I made a mistake. Here, more precisely, you get t here. I and I prime, and then here, yeah, the same thing happened. P inverse t, inverse. That's how we obtain. So that's the. So more precisely speaking, so what you end up with essentially P, T, P inverse. So that's yeah. So okay, let's start. T goes to omega in the P T transpose P inverse. That's what you get. And from one more omega, what you get is P, this guy transpose P inverse. Okay, that's what you get. And then if you apply a transpose, you get the P inverse transpose, and the T brings back, and then you get the P transpose, and this is exactly what's going to happen. Okay, so this guy is in. I think I should keep this this one in the lecture notes. Sorry. So therefore, so this P inverse transpose has to be equal to plus minus identity matrix. Okay. To get the omega square is equal to 1. Therefore, so moreover, we have some gauge equivalence between the gauge equivalence of T and then is equivalent to T tilde and the U T U inverse, where U is some unitary matrix. So this is a UN gauge group. So gauge equivalence. So then if you use this one, what you get is the so PT P transpose P inverse is equal to P U T U inverse T to the transpose P inverse. That's what you get. Yeah. And this can be understood as the P U transpose T tilde transpose U inverse transpose P inverse, and then you apply some stupid operation T tilde T U inverse transpose. I'm sorry, so I think P inverse. What I'm doing? Am I doing correct thing? Transpose P U and then U inverse. I think U inverse U. This is correct. That's correct thing to do. And this is indeed equal to this is indeed equal to why am I doing such a thing? Okay, this is equal to UT. This is equal to UP, U and inverse. So therefore, as you can easily see, this is end up with same as P tilde is equal to U P U transpose. Okay. sorry, P tilde is equal to this one, which is equivalent to P. Okay. So that's what we have done, what we have shown. So this guy can be treated P tilde, and this is P tilde inverse. Okay. So therefore, one can have a gauge equivalence to P. So we have to impose both two conditions. So this condition, and then also we have to identify equivalence. You have to impose the equivalence relation. So then it's a linear algebra to get P is either identity or P is equal to I times 0, 1, 1, 0. Nothing minus sign is involved. Like this way. There are two possibilities. Up to gauge equivalence. This gauge equivalence. And then the first choice will give you SON, as we already seen in before. The second choice will give you SPN. SPN. More precisely, n has to be equal. So since this has the how to say, the entry. Okay. Okay, so then, so if you want to introduce omega as the Oriental projection, so that you get either SO or SP, and the Oriental projection is O plus plane for SP, and O minus plane is called SO. So these two types of Oriental projection can be understood as the presence of O plane, or on the space-time filling O plane. And then one is called O plus, that corresponds to, that gives rise to SP, but the O minus gives rise to SO. So that's so we just briefly consider the bosonic string case, and then so we were going to talk about the superstring case. For superstring, so this is O minus. For superstring, let's take a look at it. So for the same thing happen for NS sector. So we will have the how to say, NS sector we have used to be graviton and gauge, the B field and then the diatom, but this one is projected out, okay, for superstring. And then NS. Oh yeah, I forgot to mention one thing, important thing. So we just considered it a type, so superstring of type from. So we have type 2B, type 2A, and type 2B. And one is peaking after just projection. You have the same chirality is opposite chirality for type 2A, but however we pick the same chirality for type 2B. And as I mentioned, so the Oriental projection identify left moving sector, mode in left moving sector and right moving sector. So therefore, one cannot simply apply the Oriental projection on type 2A because they are left moving and right moving are different mode. So one can apply Oriental only simply apply for type 2B. Type 2B. And then, so if you look at the table in the type 2 string, you have an NSR and RNS. And then HC plus 50. So I don't. 56 S and HC plus 86S coming from NSR and RNS sector in type 2B, but Oriental projection will identify only diagonal part. So from here, diagonal part survive. Diagonal part, which is the HS plus 56. 56S. Only one copy. It used to be in type 2B, you have two copies of the HC plus 56S, but only one copy will be left after Oriental projection. And what about the Ramon? The question is Ramon. So supersymmetry requires the number of the bosonic mode and ferroelectric mode is the same. So here, you have these guys are sorry, and that's coming from will give us fermion because R is fermion and S is bosonic. Okay? So NS is bosonic. This one is bosonic. And also RR is also bosonic. RR is bosonic. So we have to find, so supersymmetry requires a number of bosonic state and fermionic state. Same is the same. And then so this is 1. And how many do you have for graviton? Can anybody answer how many bosonic mode graviton have? In superstring. So in total, NS, how many NS sector? 64. 8. So NS will come from 8B times 8B. 64. And out of 64, how many of them are graviton? 35. Let me think. So it should be 8 times symmetric tracewise, right? Symmetric means you can have that diagonal element. So 45, is it correct? Then minus 1, 44. Do you agree with me? It's a 44. Do you guys agree with me? Let me check my lecture note. Sorry. Am I doing something? Sorry. 8 times 8, and then symmetric means what? It becomes, my lecture note said 35. 30, how do you get 35? Uh,
4 times 9 is 36.
4 times 9 is 36? Oh, sorry. my count. So 36 minus, okay. My formula is correct, but I cannot do the multiplication. 36 minus 1 is 35. Okay, 35. Good. Okay, and what's left? So you have to subtract 8 plus 56 minus 35 minus 1. And what's left is only possibility is this guy. So what's left is this guy. So we have the for type 2b you have 0 for Ramon. It used to be 0, 2, and anti-symmetric 4 plus. But however, these are projected out by Oriental projection. What's left is CMU. And this has 28 dimension. 28 dimension. So therefore, what we have is the essentially so this is the Latino and the Gravitino are left. This is a super partner of the graviton and the diaton, and then you have the Ramon 2 form left. And then for cross string, essentially what we have is 1 plus 35 plus, or maybe 28, 35. This is a bosonic mode of phi C mu nu and then G mu nu. So this is a bosonic, and the fermionic is that guy. 56, and then lambda minus, and psi minus mu. These are fermionic for closed string. And open string, so what we have is the 8s plus 8b. So 8b is gauge boson mu, and you have gaugino. 8s is a gaugino, superpart on gauge. I didn't use any letter for gaugino. In this lecture, let me call lambda psi, and what is the another? Let's call eta in that case. Eta. So this is gaugino for open string. So that's the spectrum for type 1 theory. However, so in type 1 theory, so this really coming from so we assume that the D9 brane exists. Space filling. Plus O plane, O9 plane. One O9 plane. So, and the question is which one does we should include, and how many D9 brane? The question is how many D9 brane. So how many D9 brane, or O plus minus, or O plus minus? So that's a question one can ask. And then most of the configuration is indeed anomalous. So that is related to so-called Green-Schwarz anomaly. So Green-Schwarz anomaly, it's related to Green-Schwarz anomaly, but I'm not going to explain what's a Green-Schwarz anomaly. But most of them are anomalous. So only n is equal to 2 to the 5. 2 to the 5 is equal to what? 32. And then O minus, O9 minus D5, D9 plane. And O9 plane. This combination is allowed. So this combination is allowed, and then so this one is called so-called. So we will see what does 5 come from? What does 5 means? 5 means that d is equal to 5 is equal to half of the dimension. So d is equal to 10, and then this exponent is half of the dimension. So this one is actually called a Tadapole cancellation. So that's what we're going to see from now. Any questions so far? So again, mostly Tadapole cancellation, we will see bosonic string. For bosonic string, instead of 2 to the 5, so this is superstring or type 1. This is type 1. This is type 1. For bosonic string, the n has to be 2 to the what? What is the half of dimension? 13. It has to be. N has to be. So we will see n has to be 2 to the 13, which is huge number. What was it? I think, did I compute 2 to 13? I don't know what the number of 2 to 13 is. I cannot even do the computation 8 times 9 over 2. So indeed this is equal to 8192. So bosonic string, it's only SO. So this will give you SO32, and this will give you SO 8192 gauge group for bosonic string. That's what you're going to see. Okay. Any questions so far? By the way, do you know how many lectures are left for this string theory? I mean, I think most of you guys want to know about the ADS-CFT, but I don't know how many will be left. Anyway, just check the Hudan calendar when is the last lecture and how many lectures are left. I have to adjust the lecture plan a little bit. Otherwise, maybe I cannot reach to the ADS-CFT. I have to skip some sections, I guess. So let's consider that, so what we are going to do is just consider open string amplitude. Open string, open and the open string amplitude. Amplitude. So more precisely, first what we are going to consider is the open string open string, which is the one loop diagram for open string. Namely, I mean, if you project to the plane, it becomes its cylinder or annulus, whichever you call it. So since it's a in the presence of brain, and then so you can have open string, and this is open string indeed one loop amplitude. Okay, so we can compute this one as before. So let's consider so W is equal to sigma plus IT. So that's our convention, and the sigma is indeed ranks full. So the sigma real part of is equal to sigma, which is inside of 0 to pi. Okay, and then so now consider it's a loop diagram. So it's a loop diagram. So open string 0 and pi, and then time direction is identified by 2 pi L. So the cylinders of radius is I consider L. So therefore, we consider W is indeed that's the identification movement. So it's almost the same as before. So what we computed is the torus amplitude. So we just consider torus amplitude for cross one loop diagram, which is end up with some factor which I already forgot. Fundamental domain, d squared tau and tau 2, and then what we obtain is some factor tau 2, I think 13, 8, tau. What did we have? 28? 48? Is it true? I need to check the precise formula. So this is cross string. I already forgot what was the precise amplitude. Yeah. Let me check up my lecture note. I didn't print out. I already forgot the fact. Yes, I think I'm correct, except, yeah, I'm correct. Yeah, I'm happy. I have not a bad memory. So this is a case. So indeed, so in this case, so the modulus is indeed L. L is the size, the modulus, metric modulus. So this is metric moduli. And then you have to find conformal Killing vector. Conformal Killing vector, of course, the time translation. So therefore, there's a one conformal Killing vector. Metric modulus, so therefore we need to introduce. So this means that the B1, B0 we need to introduce. And also, so there's a conformal Killing vector, which is just time translation. So conjugate vector is the time translation. So therefore, we need to insert one zero model from C0. So therefore, this cylinder, we call it A0C, is indeed given by dl to L over to L, which is indeed the corresponding to the fundamental integrate of a fundamental region, and then we need to include B0, C0, cos factor, and 1 in the X. In the bosonic, just now the same. Okay. So where it's really analogous to this guy. What we have done in this guy, X is trace of minus C over 24. And this, so there is a Trumpet degrees of freedom. So it's oriented coming from where it ends. So this Trumpet degrees of freedom, we can introduce I and J in the presence of N space filling plane, the 25 plane. So you get N square, and B0, C0 is also, you can compute as before. Gauss sector is equal to trace of minus 1 to the F, and then B0, C0, ghost minus C over 24, Cx, and so that's what we need to do. And this one you can, I mean, it's the same exercise we can do, which is the n square by volume 26 over 2 pi 26 and 2L alpha prime minus 13 eta IL minus 26. So L is a metric moduli. So therefore, so recall that this guy is coming from Gaussian integral. So this guy is coming from Gaussian integral of momenta, 0 mode. So you guys did for homework integral of the 0 mode of p square. So you have to do the same thing for open string, and this one is really come from Gaussian integral. Gaussian integral. And this eta is just counting the states, excited mode or level. Did I erase? Yeah. Eta really come from this. So here, instead of Q is used to be e to the pi tau, 2 pi I tau, but now we have e to the 2 pi L. That's what we get from bosonic sector. And the fermionic sector, you also have the same similar thing, but instead of, it used to be 4, but now we have only look at the holomorphic sector. So you have the eta 2 square. So that's what we get. So at the end of the day, so this guy will become so at the end of the day, so what we get is indeed H0C is equal to pi B26 over 2 pi LS 26 0 infinity dl to L to L13 eta IL 24 in the denominator. That's what we get. And remember that here you don't have the mapping cross group action, so you have to integrate over really the size of the radius goes to 0 to infinity. So you have to integrate over 0 to infinity. Okay, so let's look at the significance of this theory. So as you can easily imagine, so this open string just wipe this cylinder is equivalent to the closed string propagated on the cylinder. Okay. So it's the same as so that's called some first instance of open cross duality, so called. So you can identify that. So this amplitude is indeed just cross string propagate not infinite. Sorry. So this is from 0 to pi, but cylinder. That is the interpretation one can give in particular. So if you do the modular transformation, so tau is 1 over tau. 1 over tau is equal to, I already forgot some number, times eta tau. As far as I remember, and this number is tau 2. Let me go back to the lecture note, and then I already written down, yeah. So this is a modular property for eta dedicated eta function. If you use this property and do the following transformation, L is equal to 1 over S. L is equal to 1 over S. Then this guy can be written in square over 2 to the cube and square 2 to the 13. Really 2 to the 13 now arises. So as you can see, 2 to the 13 come from this Gaussian integral. As I mentioned, this Gaussian integral, 2 to the 13 really come from. As I mentioned, so the n has to be 2 to the 13. Okay, so this 2 to the 13 really come from this Gaussian integral when you do computation. 2 to the 13, and then so the upper factor you have 26, 2 pi ls 26, and then 0 to infinity ds over 2 over eta pi s minus 24. That's a modular property from here. And clearly, so now, sorry, I think I should put the minus. So the clearly, you can easily see that the so L goes to in here L goes to 0 has a divergence. Am I correct? Yeah. So due to this factor and so on, divergence. So now here S goes to infinity has divergence. Sorry, infinity has divergence. So divergence. And this can be understood UV divergence. This kind understood as IR divergence. So using modular property, one can always map UV divergence to IR divergence in string theory. Moreover, so this IR divergence can be understood as follows. So this, if you do the expansion for delicate end function IS, so you can just write down as follows: Q inverse plus 24 plus dot dot dot, and we just define this one is just number of state. Q to k minus 1, where k is equal to 0 to infinity, okay? Where q is equal to e to the minus 2 pi 1 over s, sorry. I think, sorry, this is okay. Minus 2 pi s. So that's, and how does this IR divergence come from? Is that you can interpret this A0C is some number from 0 to infinity ds, such that you just expand the Taylor expansion, and k e to the minus 2 pi s k minus 1 around for k equal to 0 to infinity. And this is indeed can be written as follows. So k minus s can be understood as the momentum of these states. Oh my goodness, I think p squared, I should use p squared plus mi squared. So this can be understood as energy, okay? So this can be understood, k minus 1 is, k is a level. It used to be I write the n for level, but now I use n for the number of states, so I just replace by k now. Is a level, so that essentially it counts energy. So that can be understood as like this. And if you perform this integral, so times the s, and this integral you can just consider a sum of k equal to 0 to infinity 1 over k squared plus mi squared. So this can be understood. So this IR divergence really comes from L goes to 0. Huh? Oh yeah, thank you very much. P squared, and I should call k, and also I should call k. Okay. So yeah, sorry for confusion. So we consider cylinder amplitude, and when L goes to 0, we saw when L goes to 0, we saw the UV divergence. But using modulus property of the error function, this can be understood as some particle propagating as a cross string. So if you use open cross duality, it's a schematic argument. If you use open cross duality, so its cross string goes to goes to particle limit, and then here massless field is propagating. So if m square is equal to 0, so this is clearly divergent. when of course when you take the momentum equal to zero, goes to zero. Okay, so that's the source of IR divergence once you take the modular transformation of the. So therefore, L goes to zero. UB divergence in open string can be understood in the IR divergence cross string. So here you have the so cross string is propagating and it just shrinks to the zero size and propagating as some kind of particle. And the IR divergence is S goes to infinity. IR divergence is really coming from the massless form. Massless states, a massless particle of come from of the cross string. So that's physical interpretation one can give for this divergence. And then to cure this divergence we need to include so-called unoriented worldsheet. Oh my goodness. So in addition to open string one loop amplitude, we need to consider the two type of amplitude. One is the Klein bottle. The other is the Möbius strip. So the reason will become so. In addition to cylinder, to cure this divergence, so we will consider. In addition to cylinder, we consider a Möbius strip. No, so first we will consider Klein bottle, which is something like plus the Möbius strip. So this is Klein bottle. So now this Oriental projection omega can incorporate unoriented worldsheet, and we will consider the following: Klein bottle and the Möbius strip. To cancel that divergence. Okay, that's we are going to see from the second half of the lecture. I will explain why we need to add these two to counter this divergence. So let's take a break. And then resume in 10 minutes. So, oh yeah, I need to return the homework. So do you understand what I meant about the first massive level? So you mentioned just a moment. This axon, right? But this one is projected out by so you have to incorporate this geocell projection on NS sector. And this is fermionic. And if you apply two fermionic generator, you get still they're fermionic. So therefore it's projected out. So you need to apply one more.
Okay, I see.
One more fermionic generator to have the first excited. First massive mode.
I want to ask how to see this equivalence.
How to see the equivalence? I mean. How to see that?
Or I mean, I don't understand why the new divergence for the string is equivalent to divergence for
Cross string. I mean, this is a bit schematic. Let me see. How can I explain to you? That's a good question.
它的 T 比它的又它不是一次 T， 可以做好几个 T， 好几次 T。
That's a good question. How can I explain to you? This part is a bit schematic. So it used to be Q to the Q to E to the 2 pi I tau, and then E to the 2 pi I tau. And then what we saw is this is equal to E to the 2 pi I tau 1 plus I tau 2. Like this way, right? And now I think
Well, if that means propagation has a similar formula for the amplitude.
yeah, I mean, if you compute the cross-shrink amplitude for cylinder, you should get the same formula. You should get same formula. Let's see, how can I obtain? You should get. How can I obtain that one? But here you cannot use Hamiltonian formalism. You understand why, right? You cannot write down trace of Q3 L naught. Something like that. You cannot identify like this way. So I mean, to take a trace, you have to identify top and bottom. So you cannot do that. How can I compute the cylindrical amplitude from cross-string? I should have known that. Yeah, I mean, if you have another way to compute this cylindrical amplitude, you should be able to compute. But how can I? Sorry, I cannot answer now. So I'll think about it. Yeah. I mean, I'm following this section 7 of the Polchinski's book, but even Polchinski's explanation, to be honest, I don't understand. Let me think about it a little bit. How isn't it a good way to explain how this open cross string duality? Sorry, I should have known that. So you guys need more time for homework? Okay. So I will set the time to Sunday. Is it okay? Is it enough? So you guys can work in the weekend so that you can submit on Sunday. Sunday night, maybe. Okay, I will set the time on Sunday night in that case. But this week's homework is very important indeed to understand. Sunday, 10 p.m. So I just set the deadline to Sunday 10 p.m. so that you can still have time to work on two more days. Okay. Okay, then even homework 9, I will set the Sunday 10 p.m. Yeah, okay, I set up everything Sunday 10 p.m. so you guys have time to work out the homework. But this week's homework is very important indeed. Yeah, especially homework problem 1, and then yeah, problem 2, problem 3 is relatively important, but problem 1 is the most important. Yeah. So yeah. Okay, so let's resume. So let's get started. Okay, so we are going to talk about so we're going to talk about the climb border and Mebel strip to cancel divergence. So Xuanlin answer. How do you pronounce your name? My P is horrible. Xuanlin. Okay. Ask how does this open cross duality works. I think I cannot give. This is it's coming from section 7 of the Polchinski. My argument comes from, but I think I should keep a bit more convincing. Really schematic argument I give you, but I try to give you next time. I cannot give you a bit better explanation at this moment. I will try to give you a better explanation next time, in the next lecture. Well, let's accept that and move on. So now, we have some divergence in the amplitude, and we want to cancel. That's what we're going to do. And to cancel, we consider climb bottom and have a strip. So so let's do the climb bottom. So climb bottoms, as you can, as I draw. So this is something like by L, and then if you identify them, am I doing something stupid? Yeah, I think. Yeah. So here I just assume this is 2 pi. So if you identify this one, you get the strip, and then you just identify in the opposite way. So you just identify opposite way, you get the climb bottom. I cannot draw the picture, but it's you can understand. So this is the opposite way to identify. Like it's not like a torus. Torus has to be the same orientation, but for climb bottom you get the, and this can be understood. I'll just cut in the middle and put the orientation and bring this piece. So this one part has to be identified. This part. So just bring this piece and swap this one to here, and what you get is something like this one. And this one. So let's bring this one to here. What you get is this one and this one. And this part has to be identified. This part. Okay. So that's what you're going to get. So this part is going to this part. So so this can be understood as like a cylinder. It's cylinder. But now at the end of the strip, you just identify like a. So this part is identified the opposite part. The opposite part. So namely, so this, I don't want to use red. So this yellow color should be identified white color, and the same thing happened in the opposite side. So the opposite point should be identified. So this yellow half cycle should be identified. Indeed, this point is at the same. So all these points are the same point. So as you can easily see, this point is identified with this point, and this point is identified this point. This point is identified this point. Okay. Therefore, these 4 points are indeed identical points. And then, so you just identify this yellow line and the white line. The same as yellow line and white line in the opposite. So this is really happen RP2. RP2, if you consider a sphere S2, and you just identify the antipolar point. And at the end of the day, so you can just write down RP2 as follows. So you have a disk in or northern hemisphere, but at the equator, so you just have the same situation. You have the circle here, and then the opposite side. You need to identify the opposite side in the equator. Okay, and then physicists often write that this one is cross cap. Cross cap. I mean, physicists always introduce some some fancy notation to new idea. So, but anyway, so mathematician knows from long time ago, really long time ago. But physicists newly gives the name to this identification. So this is called physicists called cross cap, and just write down like this point is identify the antipolar point, and this point identify the antipolar point, and you just do that. How to say? Just write down this X mark for cross gap stake. This like this way. That's so that's another way to see Klein bottle. So they just compare. So then this Klein model is k is indeed, so this is unoriented closed string, closed one loop amplitude. The amplitude can be written as dl. Again, you have a modulus L and trace of omega. So this omega really come from, you just identify top and bottom by just orientation flip, okay? Top and bottom. And -1 to the f. And then you can have the B0. Sorry. This is not the case. I don't think so let me erase this cross cap. B0 plus B0 bar, and then 1/2 over 2 and 2 C0 plus C0 bar, and then Q L0 plus L0 bar minus C over 24. So that's the what we are going to have. And again, here you need to include B0 bar because of the modulus of L. Okay, modulus of L. But it's cross string, you need to include both a homomorphic and an anti-homomorphic sector for cross string. And the same thing happen in the C0 and C0 bar is the time translation conform kilobacter we will have. Okay, so that's the thing. And we know that the Oriental fold action will identify B0 and then B0 bar and the C0 and the C0 bar. So this is the Oriental fold action for cross string. Therefore, this can be written as the, unfortunately, there's a typo in my lecture note. There's no 1/2 in front. The L used to be 2L. Trace -1 to the F, B0, C0, Q to the 2. That's the So you can just identify B0 and B0 bar by using Oriental projection. So that's what we are going to evaluate, and then it's the same computation we have done as before. So this one is given by 26 over 2 pi ls, 26 dl to L. So it's no longer, again, torus. It's no longer torus, okay? So it's more like the Klein bottle. So there's no mapping cross group action. Okay? Mapping cross group action. So modulus should be integral 0 to infinity. So then we have a similar problem. L cube eta 2IL 24. So that's I think we can just and also I didn't explain. So the alpha naught is identify alpha n is identify alpha n bar. So therefore L naught is identify L naught bar. That will give you 2L naught. Okay. And also its cross string is 1 over 12. Okay. So it looks really more like the open string amplitude after you introducing omega. Okay. Omega. So then one can again just counting this one coming from Gaussian integral, and then also the function comes from just counting the level, number of the level. I already erased. Maybe I'm not. It's just here k is level, so I just counting nk by the excited. And then again do the modulus transformation. This can be written. Unfortunately, I erased it. Okay, this can be written as the I. So this is S transformation. S transformation. S transformation 26 divided by 2 pi ls divided by 26. Okay. That's what we have obtained. And then ds over s eta I s minus 24. It's very similar to what we have obtained in A0C. So let me yeah. Okay, so it used to be so for cylinder, this part again 2 to this 13 show up here, and it used to be A0 cylinder will show up. This part is the n square 2 to the 13. Okay, it used to be n square 2 to the 13. Now you have 2 to the 13. And then, I mean, it's yeah. So we will see. We will see what's going to happen. So let's talk about now the Mavis strip. So Mavis strip, you just do the same thing. So we just identify top and bottom by orientation flipping. Okay. And this is equivalent to, again, is a cut in the middle. Cut in the middle, okay? Cut in the middle. And then you just bring upstairs. Okay? Bring this one and upstairs. And then what we get is the so you get this picture, and then now this part goes to this part, but just flipped, orientation flipped. And now, so this can be understood as cylinder. So this is pi now, and then here again 2 pi L, 2 pi L, okay, 2 pi L, and then 0 to pi. So now this can be understood. This is pi over 2. So this can be understood as the same as the same. So you have a you identify top and bottom, but this part is like a really you don't need to do any operation. But here again you have a cross gap state. Okay. So the physicists write down like this way. So now we have the all kind of cylinder, but the anyway cross gap state. So then, so we just consider, so A, 0 maybe strip, which is the dl over 2l trace of the omega minus 1 to the f, b0, c0, q to the l naught minus c over 12. Where Q is equal to e to the 2 pi L. And again, so this is open string. So this is unoriented. Unoriented open one loop amplitude. Okay, amplitude. Okay, amplitude, and then so yeah. So here you just using omega. You just identify top and bottom. The rest of the part is the same. So again, you have a conforming vector by time transition. You have to do C0. And you have a modulus L naught. You have to include the 0 mode for B. That's exactly the same. Now, so we have the Trumpet degrees of freedom. Now, so here, let's see. So you can have Trumpet degrees of freedom. Here you can just introduce Trumpet degrees of freedom I. Is freedom I. So naively thinking, so this part, okay. So if this point is identify this point, okay, and this point is identify this point, okay. You can see that, right? So this point identified. So therefore, as you can see, so Mabel strip has only one boundary. So Mabel strip has only one. How did it work? Oh, this come from. Sorry, this come from. So therefore, so like this way. And I think it's too confusing to my drawing. I think like this way. Yeah. So we only have one boundary. Okay. Therefore, you can only have one Trumpet degrees of freedom. So essentially, roughly speaking, so the trace of Trumpet degrees of freedom Trumpet degrees of freedom will give you n. Okay, that's the thing we need to. But it actually the sign involved depending on plus n and minus n depending on the SOSP. So let's take a look at it. Why this? So yeah, so how does omega act on this t? So omega and k, my lecture is still like as previous one, is again -1 to the n and k p t t. I think inverse, was it inverse? I already forgot. What's the case? I think as far as it should be inverse, right? Inverse. And then so therefore omega, so this can be understood as the omega acts on t is equal to omega acts on t is p t inverse p inverse. Okay. So then, so therefore, trace of omega can be understood trace of essentially t over p t transpose t inverse. Okay. And then this can be understood as so trace of this one can be understood is +1 or -1 depending on t is equal to minus t transpose. Am I wrong or I just got confused. Oh yeah, sorry. So when so this is the case when when P is equal to identity matrix, which is SO case, then this is trace of omega can be understood trace of T transpose T. That's the case, and then P is and this is equal to primes minus 1 for symmetric and antisymmetric. Antisymmetric, and then you can just but to be honest, I got confused by one thing. It shouldn't be inverse. If it is inverse, I mean, if you take trace, P and P inverse should cancel. So I think I should get just a P here. Sorry. But I don't know why. It used to be PT transpose P. As far as I remember. I don't know why I call it P transpose P. Anyway, Why did I set like this way? Gosh. Just a moment. Okay. Okay. Anyway, so it. So for p is non-trivial. For p is non-trivial. When p is non-trivial, p is I 0 minus 1 1 0. In this case, it's homework. So I think I will make it clear at this point in the homework. So yeah. So let's accept. So let's first try to understand the p equal to identity case. So then in this case, so when t is symmetric, you get the plus sign. T is anti-symmetric, you get a minus sign. So therefore, trace of omega for symmetric case is n plus 1 divided by 2 minus n minus 1 divided by 2, which is n. Okay. So this is consistent with what we have observed from the intuitive picture. You can only have the n Trumpet on degree of freedom up to sign. But indeed, so what you get, if you do that, so this is SO. So if you do the SP omega, indeed you get a minus n. So this will be exercise. I will make it clear in the homework. Okay, so then, so let's compute this amplitude. So this amplitude is the same thing. So the same computation as before. Trace of the omega, yeah, as before. It's the same as before. A0m, I don't know why, I just plus minus n. So this comes from either SO or SP. Trumpet and degree of freedom 26 over 2 pi ls 26, 26 dl over 2l, 1 over 2l cubed, 13 minus 1, 8 over 8 over il plus 1/2. Oh yeah, that's the reason why. I see. I just write down the question. 24. So the reason why I get to this 1/2 sheet as follows: you should get the minus sign after you apply omega on the Gauss sector. So therefore, what you get is indeed as follows. Indeed, so this part, I mean trace of omega minus 1 to the f B0, C0, Q to L naught minus C over 12 is indeed this numerical factor. So this is, I call it numerical factor 1 over 2L over cube, and the Q inverse product of 1 minus Q to the n and minus Q to the n over 26 and 2. So this minus sign really come from as follows. When I apply omega on the open string, alpha n is mapped to minus 1 to the n alpha n, and bn is also the same, minus 1 to the n Bn and so on. Okay, you get the minus sign, minus 1 to the n. So therefore, when you count the state with the which acts on, level n is you just apply n and we did a number of times of this exercise. Acts on vacuum states. Once you apply this omega here, you get the depending on the level, you get the minus sign. You get the minus sign due to this presence of omega. Okay. So therefore, in front of q to the n, you have to put the minus sign. Okay. So therefore, this minus sign will give you a shift plus 1/2, and an overall minus sign here. That's what you get from in the presence of the overall minus signs really come from tachyon has level minus 1. Level minus 1, you get the minus 1. Okay, so that's the reason of the 1/2 shift and minus 1. But so all in all, what we can see is as follows. I just want to keep these two blackboard and then just compare. Unfortunately, my chalk is running out. Okay, so then, so the modular transformation, this guy is indeed equal to minus plus n, and this numerical factor IB26 2 pi ls squared 26. And then after modular transformation, you get the usual factor, but you have 1/2 minus 20. That's what you get. So to sum up, is equal to n squared 2 to the 13. This one you get the 2 to the 13. You get the minus plus 2n. I think I made a mistake in the counting of numerical factor. Yeah. I made a mistake on the. Indeed, actually, there is no 2 here. There is no 2 here. dl over L. L over. Where? Okay. So in 2n and it's just numerical factor, and then numerical factor 0 infinity ds over 2, 0 infinity ds over 2, 0 infinity ds over 2, and then later is minus 24, later is minus 24, later is plus 1/2 minus 24. Okay, that's what you get from the analysis. Yeah. Yeah, it clearly makes some mistake in numerical factor. Sorry, I think there is no one half here, or maybe we need to introduce overall one half coming from overall one half in C and K. I think I will fix it later. Sorry. So you just sum them up. If you do the correct computation, you will get this factor. And then you just do the following expansion. Eta is minus 24 is q to the minus 1 plus 24 plus OQ plus dot. And the eta is plus 1/2 minus 24 is minus q to the 1/2 q to the minus 1 plus 24 plus dot. And what we are interested in, not the tachyon, but also not tachyon, but the massless states, 24 states. Okay. So divergence. So even superstring tachyon is projected out. Only we have massless states. So we are interested in looking at the massless states, and then if you sum them up, what you get is indeed what you sum them up. So this A0C plus A0K plus A0M maybe strip is n squared over 12 or 2 to the 13 minus plus and then 2 to the 13. Am I correct? Yeah. And yeah. You get this one is a numerical factor, overall factor, and this overall factor plus ds times ds times ds, and you have a tachyon states, and 24 plus dot. So this is coming from massless states. Okay, 24 coming from massless states. So to 0 to infinity, the integral to infinity ds over 2 indeed. And then to get to get rid of divergence, so you have to have n is equal to minus plus 2 to the 13 has to be equal to 0. Okay? And since n is always has to be greater than 0, and has to be equal to 2 to the 13, and SO. So therefore, to get rid of the divergence, you should have SO 2 to the 13, epsilon extreme. And this cancellation is called Tadpole cancellation. It's because as follows. What we have considered is just a cylinder, climb bottom, maybe strip, and we have essentially we just sum all the like a cylinder and the wine bottle and maybe a strip. They can be written in terms of some cylinder with some boundary. You have to have either closed cap or just without imposing anything. And then this can be understood, and this IR divergence can be understood as tadpole and without tadpole and with tadpole and square. So essentially here, this will give you, so this will give you so I think essentially this is 2 times. Okay. I think I understand what's going on. You have to include, anyway, so this up to 2 factor, this 2 factor, I need to correct it next time. I was not careful about when I write the lecture note. But anyway, if you do the correct computation, they should cancel. So that's the people has done this. So I don't think people have done. Yeah, that's we can trust. And then so this is coming. So this will give you n, and this will come 2 to the 13. And then minus n squared. This is the source n minus 2 to the 13. Okay, so that's how we obtain n is equal to 2 to 13. And the bosonic string, you can do the same computation. And now we don't need to even worry about tachyon. Okay, tachyon is projected out. And we have a massless state. Massless state is, of course, it should be now, it becomes even, instead of 24, you have only 8 and 8, okay, in here. So for superstring, I mean, it's just a, how to say, the dimensional little group. So the 26 minus 2 or 10 minus 2. And then what you end up with, instead of 13, what you end up with superstring, you become 5. Okay, the dimension d over 2. Everything comes from this factor 2 to the 13 really come from the Gaussian integral of the. So therefore, and it becomes 5. So therefore, it becomes 5. And this comes 5, and this comes 5 in superstring. And this is SO32 in superstring. And the reason why it's called tadpole cancellation is that this one is called tadpole. This one is so tadpole in quantum field theory is this guy. Okay. So quantum field theory, this guy and this guy corresponds in superstring is you can replace by this. So that's how the gauge group SO32 arises, and then SO32 arises. This analysis is actually even before this kind of analysis, and Green-Schwarz, 1982, type 1 supergravity. I'm planning to add this story to lecture note, but I don't think I can explain. Type 1 supergravity. Not 82, sorry, 84. Before 84, 1 year, there is a paper by the Witten and Alvarez Gallman about gravitational anomaly, and they pointed out type 1 supergravity has an anomaly once you compute this hexagonal anomaly. So you know, so you know the in 2 dimension in 2 dimensions you have this anomaly. In 4 dimensions you have a triangle anomaly. That's you already familiar with QFT courses. Triangle anomaly. In 6 dimensions you have a okay. And then 8 dimension this one, and then 10 dimension this guy. Yeah, sorry, 10 dimension this guy. Which one is pentagon and which one is hexagon? I already forgot. Anyway, this one, yeah. So you need to compute this kind of loop diagram to compute anomaly. The Witten and Absgame pointed out type 1 has an anomaly, but the Green-Schwartz actually found that the anomaly cancellation mechanism when the gauge group is SO32 and the E8 cross E8. E8 cross E8. That really show up the heterotic string, and also SO32 will show up type 1. Okay, so that's the one way to see how SO32 arises from. Yeah. So in the upshot, so type 1 theory is the Oriental of type 2b plus 32 D9 brane, and then 1 O9 minus plane. Okay. Okay, so that's the upshot. And one can consider, let's go, so that it's going to be very important, teleology of this theory. Okay. Now, so let's consider teleology of this theory. That's called type 1 prime, which is indeed type 2a of S1 over Z2. And now we have 32 D8 plane and 2 or 8 plane. So that's what we are going to see. So that's called type 1 prime. And this type 1 prime appear, so we will see, it's going to, I mean, it's quite miraculous. Everything works out. I mean, so the reason why, so this is the indeed low energy limit. We will see low energy limit of low energy. Low energy limit of heterotic or weak coupling limit. Oh, sorry. I think it's better to weak string coupling limit. Yeah, I think it's better to call it weak string coupling limit. Heterotic M theory. who will see. So therefore, it's very important to consider this the TDL type 1 theory. That's called type 1 prime. So let's consider TDLT and type 1 theory. So the dimension TDL acts on xi of z and z bar. So this one is TDL acts on us only acts on the homomorphic sector. So last time I explained that the TDLT, only acts on anti-homomorphic sector. You get the minus sign. And also, if you do the Oriental projection, if you also do the same Oriental projection, you just swap the anti-homomorphic and the homomorphic. So remember that in closed string, you just have alpha n is mapped to alpha n bar. Okay? So therefore, you have that's what you get. So therefore, if you perform the the TDLT and so if you perform Oriental projection and the TDLT at the same time, what you get is indeed so let's call this one is equal to x prime I z bar. So this x prime z bar is mapped to minus xi x prime z bar z. So if you apply omega on this guy, and then omega swap. What's going to happen? I got confused. So omega, so this is omega acts on this one. So let's see. So the xz minus x bar z bar is swapped to what? Is mapped to x bar z minus xz, right? And if you just swap z and z bar, then this is minus of this one, okay? You understand? And this one is indeed equal to, it's called orbifold. This operation is called orbifold. This operation called orbifold projection. So you just have the target space is identified just the minus sign, and also the worldsheet coordinate swap z and z bar. Okay, z and z bar. The anti-homomorphic and homomorphic coordinate is swapped, and that's called orbifold projection. And then what's really happening is that the so you have a circle, x9 direction is a circle, x9, so TDLT Oriental plus T duality will give you as follows. So you have the S1 with radius, this is R, and the radius alpha prime. Okay, maybe it's better to write down like this, right? Alpha prime over R as a T duality, but we need to do the following operation. So this will give you the identification at a minus sign. Just, I mean, you have a minus sign, so if it is the x direction, you have a minus sign. So it's minus sign is just you just identify opposite point and project it out. So this will give you, so S1 mod, this one is S1 mod Z2, and you have this just line. It's just projection to the line. Let's go orbital projection. And indeed, so O plane, so this O8 minus plane sits on here. O8 minus and O8 minus. And then, so it used to be, there's a D32, sorry, N is equal to 32, D9 brain, space filling brain. So therefore, there is a space filling brain. So there is a D9 brain wraps on X9 direction. Okay. So N is equal to, so this N, D9 brain wraps on this circle. But after T duality, it becomes so it spread out. As I mentioned, so if you turn on a Wilson loop, it just after T duality, it sits on some point around here, right? Okay. So D9 brain become D8 brain, a bunch of D8 brain. Okay. D8 brain. So D8 brain, if you project out, there's only 16 up here. D8 plane. There's only 16, but pre-image of this projection is 32. Okay, 32. Okay. So that's what's going to happen, and this is indeed what's going to happen. Indeed, the charge of O OP plus this is Ramon charge. So Ramon charge of OP plane, I call it mu actually. OP plane is indeed given by plus minus 2 to the p minus 4, and then charge of the p plane. Ramon charge. I introduce so mu of Ramon charge dp is indeed equal to flux of I call it h, right? hp plus 2 and s d minus p. I already forgot. 6 minus p. Yeah, 6 minus p and it's 6 minus p. That's Ramon charge I introduced in the D-plane sector, but all plane also have a Ramon charge, and that is proportional to the dp brane, but up to 2 to some factor. And if you look at the p is equal to 9, for instance 9, the charge of OP, O9 plane, minus is indeed minus of 2 to the 5. The charge of dp and D9 brane. Okay. So therefore, the Ramon charge of OP plane cancel with 32. So this 32 D9 brane Ramon charge cancel with this Ramon charge of O9 plane. So that's cool. That's one way to look at the parabol cancellation. The same thing, you can take a look at the mu of the O8 plane minus is equal to minus 2 to the 4 mu d8 plane. Okay, d8 plane. Since we have now two O8 plane sits on the edge of this Oriental projection, so 2 times O8 Raman charge is equal to 32 Raman charge of the D brane. Okay. 32 times Raman D8 brane charge. So they cancel each other. That's another way to see parabol cancellation. And then one may wonder, what happened P is less than 4? What happened P is less than 4? It becomes fractional. To cancel OP plane. And then recently, Yuji Tachikawa, I mean, it's wrong, Tachikawa and Yonekura actually explain why this fractional charge will appear by using so-called eta invariance of the RP. Eta invariance, what did I say? Eta invariance of RP, P minus 8 minus P. So this eta invariance appear as an anomaly of a fermionic anomaly of Dirac operator. That indeed cancel with these fractional charges, fractional Raman charges. So even though the string theory has been developed, lots of things. This is already 2018, as far as I remember, 2018 or 19. I already forgot. It's quite recent. We don't understand what's going on when P is equal to less than 4. Okay, less than or equal to 4. Okay, so that's a rough story. Yeah, rough story. So as you can easily see, so this so D9 brane after T30 become D8. So of course the O8 plane, O9 plane. So there's one O9 plane. Is after T duality because splits into 2 of them. Okay, 2 of them. Okay, splits in 2 of them becomes. And that will give you the end of the orbital projection. Okay, orbital projection. And the charge of the O9 plane is split into the 2. Charge of O9 plane is split into 2. Is shared by 2 O8 plane. Okay, that is consistent with this formula. And moreover. Moreover, as we will see here, actually there is a heterotic. So I will just briefly mention. So we will see heterotic string, heterotic M theory in later. I think maybe next lecture. Heterotic M theory it lives on indeed interval. So this interval. So and 10-dimensional sits in here. 10-dimensional sits in here. So this is 11-dimensional. So somehow, once you take strong coupling limit of the heterotic string, somehow it goes to M theory region. So somehow 11-dimensional open up. This segment is indeed the M theory direction. And once you take another compactification on a circle in 10-dimensional, it reduces to this type 1 theory. And then indeed this is here you can have an end of M9 plane. And also you have an M9 plane. And this M9 plane it becomes the O8. And then in fact here you have a E8 plus E8 leaves. The gauge group is E8 leaves. And 16 D8 brace goes to here, and 16 another 16, the other 16 goes to upper side. That will create somehow E8 plus E8 and the strong coupling limit of the type 1 here. And you will create some very magical phenomena for heterogamy there. Okay, that we will see later. Maybe next lecture. Next lecture I'm going to talk about the heterox string. And then, since I have lots of numerical mistakes, it looks like, so I will correct next lecture too. Okay, let's stop here.